Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to start the final leg of our journey through the world of network performance and evaluation. If you recall, we mentioned that there are three basic ways of evaluating network performance, and these are measurements, and analytical modeling, and simulation modeling. In today's session, until the end of this course, we are going to talk about simulation modeling. In the first part of this course, we basically introduced what network performance evaluation is, and we talked of the science and art of network performance evaluation. In the second part of this course, we talked about experimental network performance evaluation, in which we talked of design of experiments and many other things related to measurement of networked systems. And then in the third part of this course, we started talking about modeling based network performance evaluation. So if you see on the slide, you can see that a system can be analyzed either with an experiment on an actual system or an experiment on a surrogate or a model which is approximating the real system. And this approximation may be physical, in which you create a physical or an iconic model, or it may be a mathematical model in which we are using equations and logical relationships to represent the system. In network performance evaluation, we are mostly interested in mathematical models, and these can be implemented and either solved through analytical methods, and we've talked about this, and the prime theory we have for that is queuing theory. But in many cases, we cannot realistically model the system because the analytical modeling is limited and it cannot really capture the real system. And to avoid making many simplifying assumptions, we can actually simulate the model. That is, we can make a model and then make a computational model of it in a computer and then make sample runs of this. In other words, we do experiments on this model and see how this process evolves in time. So this has parallels to experimentation, but it must be noted that simulation is experimentation on a model. So what are the advantages of simulation? Typically, simulation is referred to pejoratively as the method of last resort. But that is a little unjust, because there are many cases in which simulation can actually outperform other methods. For example, if your system is very complex, then typically we don't have any other method except to recourse to simulations. Because in simulations, we can make our system as realistic as we want, subject to obviously spending some time on it. Because you have to, first of all, create the model, and you have to then code it in a computer system. Because while simulations can be done manually, the power of simulations is through coding on a computer and then using a computer to do sample runs on this computational model and see how the system behaves. So the prime benefit then is cost of simulation, because in many times doing actual experimentation on a system is cost prohibitive. It may be that it is also operationally impossible. You cannot disrupt the system, but you can create a realistic model as realistic as you want, and then you have complete control over it. So complete control is very important if we want to do controlled experimentation. If we want to establish causal relationships, it is necessary that we be able to control the settings that this system is working under. Also, in many cases, we can work on evaluating a system even before a prototype exists. For example, if you have something in your mind and you have no real system, obviously you cannot do a real experiment. But you can make a model of that system that you have in mind and then program it, and then with some assumptions capturing the randomness of the nature. For example, if you have a queuing system, you also have some randomness that is not in your control. For example, the arrival patterns of customers, the service time is also random. So we then use random numbers to simulate the randomness in the inherent world, and we see how the system behaves. From that, we can build a lot of intuition, and that is another benefit of simulation modeling. In analytical modeling, we can have, in a straightforward manner, steady state performance measures. But if we want to see what happens for one particular run, then analytical modeling is limited in that sense, because it talks about ensembles. It does not talk about what one sample run would be like. But using simulation modeling, we can build intuition by seeing many sample runs, and then we can generalize from that. Also, we can analyze the short-term transient behavior of a system. So simulation modeling has many benefits, and a lot of them are original benefits. We should not be saying that simulation modeling should only be the recourse when you have no other option. In fact, simulation modeling turns out that in many cases it is the only option we have. So it must be noted that simulation modeling is a lot like experimentation, except that now we are working with a model. So because of that, we have firstly the problem that what we have is not certain. The output that we are getting only applies to that particular sample run, as in experiments. Because if we do experiments, the reading that we have cannot be generalized simply on the basis of just one observation. We have to take a lot of observations and then come to a statistical conclusion. Accordingly, in a simulation as well, we cannot have exact answers as we have in analytical models that obviously make some assumptions, but they can come up with exact answers. But real systems do not subscribe completely to the assumptions of analytical models, and therefore a more realistic representation then is to have a more realistic model and see how different samples behave, and then by doing thorough statistical analysis, we can generalize from our observations. Also, because we are using a model, we have many design issues here. What amount of detail should we be having in a model is a very important question. Obviously, we want the model to be simple, because if we want to have a model that is as complex as the original system, then what is the purpose of having a model in the first place? The purpose of having a model is that it is easily understood and we can get our hands around it. We can understand it completely, and we can, in some sense, not worry about the messiness of the real world, which is very complex. But for all the extraneous details, we can remove them and then only capture the essential items and see that if that is the model of reality, what will happen for particular input parameters. So, moral of this discussion then is that we need to have proper statistical analysis of simulation outputs, and also it is very important that we have validated models that actually are a good representation of reality. More about this later in this session, and also we have a dedicated session on verification and validation of simulation models. Let me now give you an outline of today's session. We will start by talking about simulation basics and history, and thereafter I'm going to talk about some basic types of simulation models. We're going to see some classifications on the basis of which we can categorize simulation models, and we are going to see two very important types of simulation: Monte Carlo simulations and discrete event simulations. And we are also going to see one example of discrete event simulation that we do by hand to get an intuition of how computer works out a discrete event model. So let's start by talking about some simulation basics. First of all, let's talk about the application areas of simulation. The usage of simulation is very widespread, and it is used in many different industries, in many different places of decision making. Primary place that has been the driving force in the development of simulation techniques and tools has been the military. And because that is where most of the money is, and most countries are concerned about their safety. And because of that, if we have the ability to plan our war strategies beforehand, it becomes very crucial and very helpful. And therefore, the US Department of Defense has helped a lot and has invested a lot in simulation techniques and simulation tools. And many of the tools that we are using currently and the techniques that we have been born out of the efforts mainly for war efforts. One area which has really developed from war efforts is the area of operations research, in which we are trying to optimize our logistics. So, for example, we have an industry and we have certain supplies, we have demands. And all of those things are subject to uncertainty. If we could somehow simulate how things would work out for different scenarios, we would be better prepared. And that is the basic premise that helps in optimizing industrial performance. And it really has worked to the benefit, and we have improved quality as it applies to industry. Also, another industry in which simulation is big business is the entertainment industry, the gaming industry, in which we try to create a simulated reality in which different events are simulated and you can interact with those systems. For example, many of you might have interacted with flight simulators, in which you sit in the cockpit of an aeroplane and you have almost a realistic experience of actual aeroplane. Also, we have extended usage of simulations in meteorology, in the chemical industries. So there are too many applications for us to list. One way that you can find where simulation is being used is to go to the site of the Winter Simulation Conference and see how many different areas that we have there. Winter Simulation Conference is one of the most important conferences for a simulation practitioner and a researcher, and it's a very, very big conference in which hundreds of papers are presented, and hundreds of people from industry and researchers, they meet to collaborate and see how the world of simulation is progressing. We are going to be primarily be focusing on the application of simulation techniques as it is relevant to network performance. So let us trace back the history of the key ideas that we use in the current models of simulation. So for that we go back to the 1700s when we did not have any computer, but still we had the germination of the basic idea that is the bedrock of current discrete event and Monte Carlo simulations. This idea came from the French naturalist Buffon, who was working and thinking about a seemingly trivial thing. He was thinking that if we draw lines on a floor and if we randomly throw needles on the floor, what is the probability that the needle would cross a line? So this was basically a mathematical curiosity, and we did not know that this idea would become the basis of Monte Carlo sampling, Monte Carlo estimation, the creation of random numbers, and so on. This idea was then developed further and formalized by Laplace, who calculated the probability, and he said that if the length between the lines and the length of the needle is the same, then the probability is P is equal to 2 over pi. So we have the probability there. But then when we are considering a simulation, we can actually estimate the value of pi from something as simple as random throwing of needles. So the basic idea here is actually quite exquisite and quite counterintuitive. The basic idea is that if you want to estimate something that you do not know, obviously we currently know what the value of pi is, but if you have something that is very complex, you do not know how that function works, or if you have a model that has a lot of subject uncertainties and we do not know how that model would work, we can actually gain insight by doing something random. We can consider some random input and see how that model behaves. And if we were to replicate this subjection of the model to random inputs, we can actually approximate expectation of that event. So it was then seen that if we were to throw these needles multiple times, if we were to replicate this experiment multiple times, we can actually estimate the value of pi by observing how many needles actually cross the line and how many of them fall between lines. So obviously at that time Buffon and Laplace did not have computers, and it is doubtful if they actually replicated this experiment physically a lot of times, but there have been physical attempts of doing this. We are not going to do this physically, but we are going to see a simulation model of this to see how, this physical experiment can be emulated. So let's refer to the slide. You see that in the first case we throw a needle. Let's suppose it does not catch the line. So we are estimating the value of pi from the relationship that pi is equal to 2 into total number of drops divided by the number of lines hit. In this case, we have not hit any line, so our estimate of pi is infinite. So with just one random replication, we see that we cannot approximate reality very well. But if we were to do many replications, then progressively our estimate of the complex thing that we are trying to quantify progressively improves. So you can see that in the next case, the number of needles drawn is 11 and you have a better estimate. Furthermore, we keep on throwing more and more needles, and in the limiting case, according to the law of large numbers, the proportion of the needles that cut the line would converge to the probability that is defined by the mathematical relationship. So from doing experiments, we can actually estimate pi, and this is a wonderful idea. This idea was developed further and it became prominent in the 1940s during the World War. And the proponent of this scheme and the modern inventor of this was Stanislaw Ulam, who was working on the project of creating the hydrogen bomb. And he was trying to figure out the path taken by a neutron in a nuclear reaction. And it was something that could be very difficult if we use the standard methods of analytical mathematics. So he did not have a clean formula to calculate how things would work out, because there was a lot of complexity, a lot of uncertainty. So he was a very practical mathematician, and he thought that, okay, we cannot find this analytically, but what if we do experiments on this? We consider different random inputs, and then we see how the path is affected. And if we were to replicate this experiment multiple times, we can approximate the expectation of how things would work out. And this was the reincarnation of the method of statistical sampling in the modern world, and it became prominent by the name of Monte Carlo estimation or the Monte Carlo method. So because these guys were working in the Department of Defense, they had to give this project a code name. And the code name that was given to it was given by a scientist known as Metropolis, who was a colleague of Stanislaw Ulam and also a very prominent Polish American polymath, the creator of the modern architecture of computer systems, John von Neumann. These people worked together and formalized this idea of estimating something that is very complex by replicating simple things again and again, and we make use of randomness in the replications. So why did this idea become more popular, and why do we call this method as Monte Carlo method and we do not attribute it to Buffon and to Laplace? The key idea here is that the idea the time of this idea had come because of the invention of the first electronic computer, the ENIAC. And it was a behemoth, it was a big machine, and it had, for that time, a lot of computing power. So while doing this flipping of needles on the floor is clumsy, and we practically cannot do it for very long number of replications, but a computer does not get easily bored. If you ask it to do something repeatedly, it will dutifully do that. So the usage of this statistical sampling method and of repeated sampling was a perfect match for the technology that was being developed also during the World War. And von Neumann was a consultant both at the Department of Defense, the project, the Manhattan Project that was creating the hydrogen bomb, and was also working at the place where ENIAC was created. And therefore, this became the place where the Monte Carlo method was germinated. The name of Monte Carlo was chosen because Stanislaw Ulam had an uncle who often had an impulsive urge to go to Monte Carlo to gamble away. And because that has a connotation of randomness, Metropolis recommended that this project be codenamed Monte Carlo. And therefore, because of that code word, we currently refer to this method as the Monte Carlo method. Furthermore, once we had computers, the area of simulation became very prominent. It became very well entrenched in research. And in fact, you would know Len Kleinrock from the queuing theory lectures, and we know that he created a model, an analytical model for predicting the delay in a packet switch network. So let's read a quote of his to see how he actually validated his analytical results by doing repeated simulations. And he says that I established the analytical model by which you could calculate delay, and to simulate it, I had to make some fundamental assumptions. I simulated the hell out of it to show that the assumptions worked. The key idea here is, which